Hello and welcome to today's lecture on static CMOS circuits. This is the second lecture on this topic. In the last lecture, we have seen how you can extend the concept of CMOS inverter to realize NAND gates and NOR gates, and we have studied the characteristics of those NAND and NOR gates, and here is the agenda of today's lecture. Of course, before giving the agenda of today's lecture, here is a brief recap what we discussed in the last lecture, and or rather we can summarize what we discussed in the last lecture. We have seen that transfer characteristic does not remain symmetric with increase in fan in of the gates. That means, when you are realizing 2 input NAND gate, 3 input NAND gate, or 2 input NOR gate or 3 input NOR gate, and as you are increasing, the transfer characteristic becomes asymmetric. That means, the switching point of the gate moves either towards left or towards right. Second, our second observation was, for the same area, NAND gates are superior to NOR gates in switching characteristics. We have seen that if we realize gates with minimum area, then NAND gates are superior to NOR gates in terms of switching characteristics, of course, area remaining same. Also, we have seen, for the same delay, NAND gates require smaller area than NOR gates. That means, if the area is not a constraint, if we want the NAND and NOR gates should perform equally in terms of switching characteristics, then with increased area for the NOR gates, we can achieve same performance for both NAND and NOR gates. Our fourth observation was, noise margin and switching characteristics are better for NAND gates compared to NOR gates. So, because of all these features, obviously NAND gates are faster and better alternative to NOR gates. However, whenever you go for realizing real life circuits, you will see that both NAND and NOR gates are used as part of the standard cell library, because in whenever you are realizing a complex circuit, it is not the delay of an individual gate, but the delay of the entire circuit is important. So, in that context, we shall consider a combinational circuits. Obviously, inside this circuit we have a complex network of different types of gates, maybe combination of NAND, NOR, AND or exclusive or different types of gates. And here are the two important characteristics of combinational circuits. Number one is, combinational circuits perform Boolean operations on multiple input variables and produces output as Boolean functions of the input variables. Now, you may be asking, what is the number of primary inputs which are used in present day VLI circuits? You will be surprised to note that the number of inputs of present day combinational circuits can be as high as 100 or even 150. That means, the number of inputs fan into the combinational circuit is increasing, and whenever you are realizing a combinational circuit with such a large fan in, obviously it cannot be realized by a single gate. You have to realize by a network of gates. Then second characteristic is, it generates output based on the input values after a certain time delay and preserves the output as long as power supply is provided. That means, this is another characteristic of combinational circuits, that means output is dependent on the primary inputs, not on past history. However, output value that we get will be obtained after certain delay, because the combinational circuit will have some finite delay. As we have seen, even a single gate, NAND gate or NOR gate has some finite delay. Whenever you are realizing a circuit with a complex network of gates, obviously delay will be larger, maybe 3 or 4 gate delays or more. That means, it will be a multi-level network gate realization. And another point is, output remains steady as long as power supply is provided, and that is particularly true for static CMOS circuits. Later on we shall see there is another version, as I mentioned, dynamic CMOS circuits, which is a which also realizes combinational circuit, but there you will see that output will change unless it is refreshed at regular interval, but that we shall discuss later on. Okay. Now, let us have a look at the general CMOS logic circuit structure. We have already seen how you can realize NAND and NOR gates. We have seen that NAND and NOR gates idea, multi-put NAND and NOR gate concept can be extended to realize any complex CMOS circuit, where the general logic circuit structure is like this. Let me redraw it again. So, that you have got a PMOS pull up network, and which is connected to the supply voltage VDD, and you have a NMOS pull down network which is connected to ground. Output is taken from the junction of the PMOS network and NMOS network, and common inputs are applied to both the PMOS and NMOS circuit. And we have already seen how you can realize NAND and NOR gates. For example, a 2 input NAND gate. A 2 input NAND gate we have seen will require a network of 2 PMOS transistors and a network of 2 NMOS transistors in series. So, here you will apply, let us assume A, B, and you will take output from here. So, this is your PMOS network, that means this part is your PMOS network which is connected to VDD, and this is your NMOS network which is connected to ground, and you are taking output from here. Now, what is the role of the PMOS network? Role of PMOS network. So, what is the role of PMOS network is to, as the name suggests, it is a pull up circuits, that means it pulls up the output capacitance voltage to VDD level. That means the load capacitance which is connected to the output, it pulls it up to VDD. In other words, the output, whenever you are expecting an output 1, then there will be a path through the PMOS network. That means, PMOS network will be on whenever output is supposed to be 1. In fact, you can do the logic design based on that idea. Similarly, what is the role of NMOS network? So, role of PMOS network is to pull the output to high level, and role of NMOS network is to pull the output, pull down the output to low level. So, based on this you can essentially realize a circuit. That means, when the output is to be 1, this PMOS network will be on, there will be path of VDD to the capacitor. Similarly, when the output is to be 0, it will be 0 for a given input combination, the path will be through the NMOS network. This is how you can realize a circuit. Now, let us take off some examples. How can I realize AND and OR gates? We have already discussed the realization of NAND gates. Now, let us consider the realization of AND gate. As we have seen, the realization of NAND and NOR gates come very naturally to static CMOS circuits. We have seen you will just realize a series connection of NMOS transistors and a parallel connection of NMOS transistors and realize the circuit. And output function in this particular case, that means NAND 2, the output function is represented by A dot B dot. If you consider the truth table, will be, we have got 2 inputs, there will be 4 combinations 0, 1, 1, 0 and 1, 1. So, for NAND gate, the output V out will be output 0 whenever input is 1, 1, in rest of the cases output is 1. So, we find that output will be 1 whenever you apply any input combinations like 0, 0, 0, 1 and 1, 0. That means, whenever you apply these inputs, a path has to be established for through the PMOS network. How it can be done? As you know, when we apply 0 to a PMOS transistor, it turns on. So, we find that if any one of the 2 transistor is if we apply 0 to any one of the 2 transistors, output will be 1. And in fact, that is the reason why we apply, you can realize based on that. If you simplify this, you will get essentially, if we combine these two, you will get A bar and here you will get B bar. So, essentially you are applying A bar and B bar and you are realizing this part of the network. Similarly, for 1, 1 output will be 0. As you can see, 1, 1 means you will require 2 transistors in series, and whenever both of them are 1, 1 output will be 0. And this is the function f that it realizes, and if you represent it, it will be in expanded form A plus plus V plus. One important characteristic of this is, you see, all the output function in the minimized form has got its literals, that means A and B, in complemented form. What kind of function it is? In all of you must have attended a course on switching circuits and logic design, and you have been introduced different types of logic functions. You may recall that a Boolean function can be say unit. You may have heard the term unit. What do you really meant by unit? When do we call a function unit? Unit is a function is unit when the literals come either in complemented or in uncomplemented form. That means, for example, A is present here in uncomplemented form, B and C both are present here in complemented form. So, this is a unit function, but if another function you write, say f2, which where it is A dash plus B C dash plus B dash B C or say A B, let us assume this is the function. In this case, as you can see, A is appearing both in complemented and uncomplemented form, B is also appearing in complemented and uncomplemented form. So, it is not a unit function. On the other hand, if all the variables appear in uncomplemented form, say A plus B C, where none of the variables has appeared in complemented form. So, it is called positive unit function, positive unit function. And similarly, F4, which is say A dash plus B dash plus C dash, where all the variables have appeared in complemented form, it is called negative unit function. And in fact, for unit function these expressions are there is no alternative, that means these representations are unique, that means minimal sum of product form is unique. So, they are the canonical representation of the function. So, you can see here F3 where all the variables are in non complemented form and here all are complemented form. Now, if you look at this realize the function of the NAND gate, what does it tell? Both the variables have appeared in complemented form. That means, whenever you are realizing a function f and you are applying some inputs here, it will be a negative function of the inputs. That means, a CMOS gate realizes a negative unit function in terms of its input variables. That means, all the variables will be in complemented form. We have diverted to this, the reason is whenever you are realizing AND gate, it is not so. Whenever you are realizing AND gate, f is equal to a b. Obviously, you cannot really realize an AND gate without just by applying a and b. Of course, you can use De Morgan's law to represent it in different ways. For example, you can have it, you can represent it in this way, a dash plus b dash bar. So, now you can realize this one, this function can be realized, a dash plus b dash bar. So, now you can see the functions are in complemented form, the inputs. That means, you can realize an AND gate in this way. Obviously, you will realize, you will require two PMOS transistors and two NMOS transistors, and to the NMOS transistors the inputs will be a dash and b dash. Here also you will apply a dash and b dash. So, here it will realize a b, essentially it is realizing this a dash plus b dash bar. So, here we have assumed that the complemented variables are available as inputs, but if the complemented variables are not available as inputs, how can you realize it? Another alternative realization is by using, what you can do, you can realize f is equal to a b bar, bar. That means, you will be realizing an NAND gate and put an inverter. For example, you already know how you can realize a NAND gate, to input NAND gate. Sorry, you will realize NAND gate, you will require two PMOS transistors in parallel and two NMOS transistors in series. So, here you will apply A, B, and this is connected to ground. Then of course, at the output you will again require an inverter, because here it realizes A B bar. So, that has to be complemented to get the function of a of an AND gate. So, here you will get A B. So, here you see you can realize AND gate in two ways. This is how you can realize when the inputs are available in complemented form, also in complemented form. On the other hand, if the inputs are not available in complemented form, then you will require two levels of realization, because in the first level you will realize NAND gate to input NAND gate, and you will invert it to get the AND function. So, both are possible. However, the second type, this will require larger delay, but this will require invert the complemented inputs as must be available to you. If the complemented inputs are not available, this is how you can realize. So, both the configurations are used in practical realization. In a similar way, that means what you have done here. So, you have expressed the functions in terms of two, this is realizing a negative function, this is realizing a negative function, because this whatever is input, it gives a bar complement of that. So, you can see essentially you have expressed the function in terms of negative functions. You have decomposed the function in terms of negative functions. In fact, there is sometime, I mean, back in 70s, a lot of research were carried out to realize CMOS combinational circuits by expressing it in terms of negative unit functions. Anyway, this is how you can realize AND gates. Now, let us consider the realization of OR gate. In a similar way, OR function is equal to f is equal to a or b. It can be represented as a bar and b bar bar. So, this is how you can represent it by following De Morgan's law, and corresponding realization is you will require an OR gate in this way, a bar and b bar. So, you will require AND. So, a bar b bar, and here it will be just the. So, we find that in this particular case also you are applying complemented inputs, because this is a positive unit function. A positive unit function cannot be directly realized by a CMOS gate. So, you have applied complemented inputs to realize OR function. Of course, you can realize it in a different way, as I have already told. You can realize the NOR gate first. You can realize NOR gate. This is a typical NOR gate realization, A, B, and then put an inverter. So, this is an alternative realization for OR gate. So, that means, here you are realizing A or B NOR function, then here you are getting OR function. So, this is how you can realize OR gate. Now, from this what can I say? We can realize AND gate and OR gate and also some complex functions, but can we realize any unconventional function? So, we have seen in terms of NAND gate, NOR gate, OR gate, AND gate realizations we have seen. Can we realize any complex function by extending the idea that we have discussed so far? So, that can be done. You can realize any complex circuit. For example, you have to realize a function f is equal to a dash plus b c. This is not a positive unit function or a negative unit function. How can you realize this? So, we have seen from this realization what it really does, or if we consider what this part of the circuit does. This part of the circuit realizes the complement network. This is the complement. So, a dash a bar plus b bar. So, this is the NMOS network realizes the complement function, and the PMOS network is essentially dual of the function, the dual of that network. Dual means whenever it is series, it is parallel, whenever it is parallel, it is series. So, that is the concept that we can use to realize any complex functions like this. So, this can be realized in this way, this can be expressed in this form, a dot B dot or C dot, then you can complement it. So, the complement is A and B dash plus C dash and then complement of this is how F can be represented. So, what is the corresponding realization? This is the network, NMOS network. So, NMOS network will be the series of A and you will apply B bar, C bar in parallel, then connect it to ground. So, this will be your NMOS network. So, the PMOS network, so it is the complement of the function. So, and the PMOS network will be dual of this network. So, there it will be this is in series. So, A will be applied parallel, here we will apply A and these two here they are in parallel, they will be in series. So, you will connect it to VDD and you will take output from here. So, this realizes F, that means here the PMOS network is dual of the NMOS network. You will apply the same input A, B dash, C dash. So, they are in series and then you will get the function. So, we find that this is how you can realize any complex function. So, we have extended the basic idea of realizing simple gates to realize complex gate. You may be asking why you should go for realizing complex gates. The reason for that is there are two basic approaches. One is you can use standard cells to realize any given Boolean function. So, in that case the delay can be quite long. On the other hand, if you realize a complex CMOS circuit, but it should not be very complex, that means the number of transistors in series and parallel should not be very large. So, maybe up to 4 transistors in series and 4 transistors in parallel will be allowed. Beyond that delay will be too long. So, as long as the number of inputs remain within 3 or 4 and function is complex, you can realize any Boolean function using this approach. Let us see how it can be done. Essentially, there are two basic approaches or rather two basic topologies. One is known as AND or invert, one approach is known as AND or invert, in short AOI. This is one approach. That means, you can express the function in terms of AND or invert. For example, say we realize a function y is equal to A, B plus C. So, this is a and you could have put D also here. Then, so AND of two product terms or of them and then complement. So, AND or invert. So, this particular function can be realized by using you can realize it, you can implement it by following the corresponding topology will be say AB will be in series, then CD will be also in series and they are in parallel. So, this will be your NMOS network using AND or invert approach, and corresponding PMOS network will be just the complement of it. Complement means A and B will now be in parallel. So, A and B will be in parallel and C and D also will be in parallel. So, this is D, this is C. and you will take the output from here, this will be connected to VDD and this will be connected to output. So, this realizes Y. So, following AND or invert approach, you can realize a function in this manner. Similarly, you can also use another approach depending on the representation of the function. We know there are two possible minimal form. One is known as sum of product. This is essentially complement of the sum of product. Another is product of sum. That means, it can be like this, say A plus B into C plus D. So, here you have taken the product of sum, that means, and if the function is like this and complement of this can be realized very easily. For example, there the corresponding topology, this function will be realized in this way. So, you will be having A and B in parallel, A, B connected to ground, and C and D again in parallel, C and D in parallel, and this will form the NMOS network, and PMOS network will be the dual of that. That means, A and B will be in series, A and B will be in series, and C and D also will be in series, and they will be in parallel. So, there is C and D, and here it is your VDD. So, this suppose this is your F. So, this realizes F. So, this is the corresponding OR and invert topology. That means, you can use one of the two topologies for realizing a Boolean function. You can either represent in sum of product form or product of sum form to realize the complex CMOS function using one of the two topologies, AND or invert or AND or invert. So, this is in short OAI, or AND invert. But in all the cases, as I told, the output is a negative function, realizes a negative function irrespective of the way you are realizing the circuit, maybe in AND or invert topology or by using OR and invert topology, the function is negative in terms of the inputs. Let us take up an example, complex CMOS XOR gate. So, here the realization of a CMOS XOR gate is shown. Here you can see XOR function has been realized in AND or invert form. AND or invert means AB or A bar B bar. Sorry, this is I have a mistake. These will be negative. These will be. Let me draw it here. There is some mistake there. These are NMOS. By mistake, it has become CMOS. Say XOR gate. XOR. You are realizing XOR function. Now, XOR function, as you know, F is equal to A bar B plus B bar A, or it is also represented as A exclusive or B. Now, you can realize it in this manner. You can, by using the Boolean algebra, you can express it in this form, say A B plus A dash B dash bar. So, either it can be represented in this way, or it can be represented as A plus B dash into A dash or B and then complement of it. So, depending on that, you can have AND or invert, or and invert topology. Say let us first consider the realization corresponding to this AND or invert. So, here you have got A B, this is A, this is B, and here A dash, B dash, and then this is your NMOS network. Corresponding PMOS network will be, these two will be in parallel. So, A, B, similarly A dash, B dash, A dash, B dash, and you will take output from here. So, this is the realizing A exclusive or B in AND or invert, using AND or invert topology. You can also realize based on this topology. In that case, you will apply A in parallel with B dash, similarly A dash, B connected to ground, and on the corresponding PMOS network will be A and B bar will be in series, A, B bar they will be in series. Similarly, A bar B, A bar B will be in series, and VDD is connected here, ground is connected here. So, this is AND or invert realization, and this is OR OAI or AND invert realization. So, you can see both are possible. XOR function has been realized using both the topologies. So, in terms of, in this particular case, in terms of area, in terms of delay, it will be more or less same, because there are two transistors in parallel or two transistors in series, but there is a possibility that one of the two topologies may be superior in switching characteristic. In this particular case, that is not true, but it may be possible to have realization in which one of the two topologies will be superior. Now, we shall consider the realization of a little more complex function, that is your full adder. As you know, adder is one of the most common functional element you require in any circuit that performs computation. So, adder, subtractor, as you know, using 2's complement form, subtraction can be implemented by using addition. Similarly, to realize multiplication, division, you will require addition. So, adder is the most common building block of arithmetic and logic unit of any processor. So, a lot of research has been carried out to realize adder. Of course, I shall consider the simplest adder, that is known as ripple carry adder. What you do in ripple carry adder, say you apply some input A, say let us assume you are applying A0, B0, here you are applying input C0, and it produces C1 sum and carry, and that goes to the next stage. Sorry, sum is available here, sum you can say as is available here, S0, it will not go to the next stage, and C1 will go there, and you will apply A1, B1, and with C1 as input to it, and it will produce S0, S1, and it will produce C2, and it will continue. Ultimately, it will realize a n input adder. So, it will be n s n minus 1, and this is the carry generated by that stage C n minus 1, and here of course, you are applying a sorry, it will be C n, and it is a n minus 1, b n minus 1. So, you can see you are using similar building block, these are known as full adder. This is a full adder. So, full adder means it has got 3 inputs, a 2 variables and a carry from the previous stage, and it produces carry and sum. So, if we can realize one full adder by using complex CMOS circuit, you can cascade them to realize a adder of n bit adder. So, I shall discuss about realization of a single bit full adder. Single bit full adder means you will apply ai, bi and ci minus 1 as ai, bi, ci as input, and it will produce sum and carry. That means, your requirement is to realize a full adder cell, you can say, where you will apply say ai, bi and ci, these are the 3 inputs, and it produces 2 outputs Si and Ci plus 1. Ci plus will go as input to the next stage. So, how we can realize this? We know that the carry function Ci plus 1 will be equal to ai plus ai and bi plus ci into ai plus bi. That means, whenever any 2 inputs are 1, it produces a carry. Similarly, it produces a sum Si whenever any one of the inputs is 1. That means it is like this, say A in dash, B in dash, C in. That means, if Ci. So, this is one of the inputs is 1, or it can be A in Ai, B Ai, Bi, Ci, that means, in this case, say this is complement, this is complement, or it can be say Ai, Bi, Ci, say in this case this is 1, this is 1, so this is 1, or say odd number of inputs are 1. That means, it can be also sum will be 1 whenever Ai bar dot Bi bar dot Ci bar, and this can be simplified to represent in this form. That means, this not this, I have put it wrongly. So, these complements will not be here. Odd number of ones means 3 ones. So, Ai, Bi, Ci, or Ci plus 1 dash Ai plus Bi plus Ci. So, you can see it has been simplified, and we have used the carry as the input to the next stage. So, this can be used to realize, but what we shall do, we shall realize this in sum of product form. So, we shall realize the complement, then use an inverter. So, these are positive unit functions. So, what we shall do, we shall follow this approach, that means, where we have used the this kind of approach, where we are using inverter at the output. So, this kind of approach we shall follow to realize this. So, let me show it here itself. Here for the sake of simplicity, these IAs are not there. Here input is A and B, input is C in, and S is sum, and C0 is the carry output. So, carry in, carry output, and A and B are the inputs, and sum is S is the sum, and CO is the carry output. So, first the carry function has been realized in AND or invert form. So, this is the corresponding function A and B, that is in series, A and B is in series, then C in and A and B in series in parallel, and this is the NMOS network, and corresponding PMOS network is the dual of this. So, you have got A and B in parallel, and A bar A and B, these A and B are in series in parallel with C in, and here of course, we shall get C 0 dash, not C 0. The reason for that, complement of this is realized by this network. So, this is how we have obtained the realization of the carry function, and of course, you will require an inverter. An inverter is required to produce the carry that will go to the next stage. Then this is used as input to the next stage, to the circuit that realizes the sum. So, here you can see this A, B, C in this particular part, this product term, this is the corresponding network, here is the network, and this C in dash network is here. So, the corresponding NMOS network is shown here, A, B, C in parallel, A, B, C in parallel, that is in series with C 0 bar, and A, B, C in, that is in series, that is in parallel to this OR is there. So, parallel to this, and corresponding dual is the PMOS network. Of course, here it realizes the complement of sum. So, you will require an inverter to realize sum S. So, how many transistors are required to realize a full adder circuit? So, here we see 5 plus 5 10, and this requires 3 plus 3 7 plus 7 14 plus 10 24, and then 4 requires 2 inverters. That means, you require 28 transistors to realize this full adder cell. So, this is how you can realize a full adder circuit. Now, we find that in case of full adder, the total number of transistors in any gate is equal to 2n. If n is the number of inputs, you will require 2n as the number of transistors, considering both PMOS and NMOS transistors. And also it will the next stage also the output will go to the next stage, where you have to connect it to the NMOS as well as PMOS transistors. And as a consequence, the CMOS circuits are very robust. We have seen the it has got a very good noise margin, power dissipation is small, but it requires very large area and delay is larger. So, what is the way out? There is another way of realizing CMOS circuit. I have already discussed about that, that is your pseudo-nMOS. Let us have a look at the pseudo-nMOS circuit. So, here is the realization of a pseudo-nMOS NAND gate, and here is the realization of a pseudo-nMOS NOR gate, and these are the realizations corresponding this is the realization of pseudo-nMOS XOR gate, and this is the realization of that function that I discussed. So, we find that number of transistors is not 2n plus n plus 1. That means, the number of transistors required in case of pseudo-nMOS is not 2n for realizing a function of with fan-in of n, but n plus 1. So, that is a significant saving whenever you consider realization of functions with large number of fan-in, say 100 inputs. So, instead of 200 transistors, you will require 101 transistors. Not only that, it will drive to, I mean each output will drive to only one transistor, NMOS transistor. It will not go to the PMOS transistors, because there is PMOS transistor is there is only one PMOS transistor which is grounded. So, we find that an n input pseudo NMOS requires n plus 1 transistors compared to 2n transistors of the corresponding static CMOS gates, and this will lead to significant and substantial reduction in area and delay. What I am trying to tell, that pseudo NMOS circuits will be faster in operation, because the intrinsic capacitance will be smaller and also the number of transistors will be smaller. So, area, capacitance both are smaller. So, pseudo NMOS circuits are faster in operation, smaller in area compared to static CMOS circuits. But unfortunately, it has got a very serious limitation. What is that serious limitation? As you know, when the output is 0, that time this pull up net transistor is on, pull down transistor is also on, and as a consequence there will be static current flow through this path. So, because of this static current flow, there will be large power dissipation. So, we are discussing about low power circuits. Obviously, the pseudo NMOS circuits cannot be used for low power applications because of large static power dissipation. So, what we can do? Can we achieve best of both the worlds? That means the robustness, that means the lower area of pseudo NMOS, faster operation of pseudo NMOS, but lower power dissipation of CMOS. Can we achieve that? In fact, that can be achieved with the help of dynamic CMOS circuits. So, we can summarize what we have discussed today. We have seen that complex logic gates can be realized using either AND or invert or and invert topology. We have discussed how it can be done, and we have mentioned that static CMOS circuits occupy larger chip area than the pseudo NMOS circuits. We have also seen static CMOS circuits are slower than pseudo NMOS circuits because of smaller capacitance of pseudo NMOS circuits and smaller area. However, as I have told, pseudo NMOS circuits have static power dissipation, and as I have mentioned, dynamic CMOS circuits combine low power of static CMOS, smaller chip area and faster operation of pseudo NMOS circuits. So, that will be our that is what we shall discuss in my next lecture. We shall discuss about dynamic CMOS circuits, and we shall see how best of both the worlds of static CMOS and pseudo NMOS can be combined in realizing dynamic CMOS circuits. Thank you.